So today we're going to be talking about the cubic function. So you can see that the original parent function is equal to f of x is equal to x cubed. So when x equals -3, if we were to put -3 in for x here, we would get -3 cubed, which we know is -3 times -3 times -3, which would be 9 times -3, which is -27. -2 cubed would be -2 times -2 times -2, which we know is -8. -1 cubed is -1 times -1 times -1, which we know is -1. 0 cubed is 0 times 0 times 0, which we know is 0. 1 cubed is 1 times 1 times 1, which is 1. 2 cubed is 2 times 2 times 2, which is 8. And 3 cubed is 3 times 3 times 3, which is 27. So now if we were to graph these points on the graph that we have to the left here, we would have point -3, -27, which would be way down there, so we're not going to be able to graph that on here. We'd have point -2, -8, so we have 1, 2, 3, 4, 5, 6, 7, 8, 0 point here. We'd have point -1, -1, which is right here. We have point 0, 0, 1, 1, and 2, 8. And this is what our cubic function looks like. So now here are some basic characteristics of our cubic function. So we can see here that the shape kind of looks like a vertical squiggle. The degree is a degree of 3. The end behavior is what is happening at the ends of the graph. So as x approaches positive infinity, which is to the right, it's going up, towards positive infinity. As x approaches infinity, f of x approaches infinity. As x approaches negative infinity, which is to the left, it is going down to negative infinity. As x approaches negative infinity, f of x approaches negative infinity. Number of turning points. Remember, a turning point is when a graph goes from increasing to decreasing or decreasing to increasing. If you look at our graph here, our original parent function is always increasing. Our center point is 0, 0. Our symmetry is about the origin. So what that means is if I were to draw a diagonal line, it would be symmetrical about this diagonal line. The domain is all real numbers. The range is all real numbers. So what this means, the domain is all real numbers. It touches all possible x values. The range is all real numbers, meaning it goes from low to high. It is increasing everywhere, decreasing never. The x-intercept is just here as 0, 0. And here are just a few exact points. So it touches point -1, -1, 0, 0, 1, 1, just a few to keep in mind. Pause the video here if you need to finish copying these down. All right, so there are a couple terms that we need to go over here. This term right here is our leading coefficient. This term right here is our cubic term, and that's our degree right here. This is our quadratic term. This is our linear term. And this is our constant term. Pause the video here that you need. Some basic vocabulary for a cubic function. Factor. A binomial that divides into a function evenly. An even factor is when degree is even, it causes a bounce on the x-axis. An odd factor is when a degree is odd and causes a function to cross the x-axis. So let's think about this for a second. If you think about a quadratic function, we know that that has a even degree. If you think about a quadratic function looks like this, meaning it bounces off the x-axis if you're thinking about the original parent function. If you think about our cubic function that we just drew over here, it has an odd degree and it crosses through the x-axis. The 0 is a value that makes the function equal to 0. Other names for the 0 are solutions, x-intercepts, and roots. So if we were to turn these zeros into factors, which is backwards from what we did in our last unit, we would subtract 1 to both sides. We would get x minus 1 equals 0, and x minus 1 would be our factor. So here, we would add 4 to both sides, and x equals x plus 4. 0, and x plus 4 would be our factor. And then for this one, we'd have to multiply both sides by 3 to get 3x equals negative 2, and then add 2 to get our factor to be 3x plus 2 equals 0, and this would be our factor here. So now working backwards, if we were turning our factors into zeros, you know this would equal 5. If we were to set this equals 0, this one would equal negative 3, and this one, let's show a little bit of work, 4x minus 5 equals 0. We add 5 to both sides. We get 4x equals 5. Divide both sides by 4. And x would equal 5 over 4. And this would be our answer. A turning point is a change in direction on a graph. The local or relative maximum is a point on the graph that is higher than all nearby points, and a local or relative minimum is a point on the graph that is lower than all nearby points. So if you remember from our previous units, our local maximum or our relative maximum, which mean the same thing, are all of our bumps in the graph. Our local or our relative minimum are all the valleys in the graph. All right, so this would be, we had something like this. That would be a local maximum, that would be a local maximum. We had something like this would be a local minimum, this would be a local minimum, and so on. Now moving on to our types of polynomials. So when you have a degree of 0, which means that f of x is just equal to some kind of constant, some kind of number, this type of polynomial is a constant. And the shape is just a horizontal line. If your polynomial has a degree of 1, we know what this formula looks like. It's our y equals mx plus b formula, so this is linear, which means it's a line that's not horizontal. Okay. And here we know what this function looks like. It has a degree of 2. We know this is a quadratic. Which we all know looks like this. With a degree of 3, this is cubic, which looks like this. And with a degree of 4, this is quartic, which is going to end up looking like this. Now for this example, I want you all to turn to your partner and I want you exploring this on Desmos together. So what I mean by this is your leading coefficient here is 1. we can see that our degree is 3. And because we did the first example problem together, we know that the cubic function that we just graphed before looks like this. So as x goes to positive infinity, our function goes up towards positive infinity. And as x goes to negative infinity, our function goes down. As it goes to the left, it goes down to negative infinity. All right, so I want you to pause the video here. And for about 5 minutes with your partner, I want you going over in Desmos how to graph all of these, what the leading coefficient is, and where the end behavior is. And then we will go over it in this video together. After you've explored these problems with your partner, you should have gotten that this leading coefficient is -1, and our degree is 3. Our end behavior is negative infinity and positive infinity, respectively. Here, our leading coefficient is 2. Our degree is 4. And as x approaches positive infinity, f of x approaches positive infinity. And as x approaches negative infinity, f of x approaches positive infinity. For our next one, our leading coefficient is -2, and our degree is 4. And as x approaches positive infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches negative infinity. For this one, our leading coefficient is -1, and our degree is 5. As x approaches positive infinity, f of x approaches negative infinity. And as x approaches negative infinity, f of x approaches positive infinity. Here, our leading coefficient is 1, and our degree is 6. As x approaches positive infinity, f of x approaches positive infinity. As x approaches negative infinity, f of x approaches positive infinity. For this one, this is an intercept form, but we understand this is a quadratic function, especially since we just finished our quadratic unit. So we know that since there are two x's multiplying together here, our degree is going to be 2. And because of this 2 out front, our leading coefficient is going to be 2, which makes as x approach positive infinity, f of x approach positive infinity. As x approaches negative infinity, f of x approaches positive infinity. And here you see we have 3 x's, which gives us a degree of 3, and a leading coefficient of 1/3, which makes as x approach positive infinity, f of x approach positive infinity. And as x approaches negative infinity, f of x approaches negative infinity. So, we want to realize something here. Whenever our leading coefficient is positive and even, both of our end behaviors go up. Whenever our leading coefficient is negative and even, both of our endpoints go down. Whenever our leading coefficient is positive and odd, they go in different directions. Whenever our leading coefficient is negative and our degree is odd, they also go in different directions. So let's talk about what all of this means. So when you have an even degree, think about your quadratic function, all right? When you have an even degree, both of your endpoints are going the same direction. When the leading coefficient is positive, that direction will be positive infinity and positive infinity. When our leading coefficient is negative, this will be negative infinity and negative infinity. Now, when our degree is odd, think about our cubic function. They're going to go in different directions. When a degree is odd and the leading coefficient is positive, positive will go with positive and negative will go with negative. When our degree is odd and our leading coefficient is negative, it is the opposite. So now let's talk about the directions for graphing a polynomial. Step 1, determine the end behavior. Step 2, find the y-intercept by setting x equal to 0. Step 3, find the x-intercept. Step by setting y equal to 0. There are also your zeros. A calculator may help. Determine if your zeros bounce or cross. Graph all zeros. Identify your max and min using a calculator if needed.
Now let's move on to example number 4. So we can see here that we have an odd function because we have a degree of 3, which you can see right here. So our function is odd. Our function is going to be positive because our leading coefficient is positive. We know there's nothing here, so it's implied to be just 1. Which is going to tell us that as x approaches positive infinity, f of x is going to approach positive infinity, and as x approaches negative infinity, f of x is going to approach negative infinity. So for this problem, I am going to allow you to use either a graphing calculator or Desmos, so please take that out now. Once you have those things out, this problem is going to be fairly easy to graph. So once you have Desmos or your calculator to graph this, you should have a point approximately here, approximately here, approximately here. And like I said, this is just straight from Desmos and your graphing calculator. So you're going to have something that looks like this. All right. Your y-intercept you get when x equals 0. So if you press Control-T in your calculator or you scroll over the point on Desmos, you'll see that it crosses the y-axis here at 0, 4. So using Desmos, you can either scroll over the x-axis and see where y equals 0 on here to figure out what those points are, or on your graphing calculator, if you go to Menu, Analyze Graph, and then hit zeros and find the zeros the same way that we found our intersections, you should be able to find them that way as well. So when you do that, you're going to get your zeros to be 0.732, 0, 20, negative 2.730. So again, the way you would find these zeros in the calculator is by going to Menu, Analyze Graph, hitting zeros, and then highlighting each of the zeros individually to get these points, just like how we did when we were finding our intersections last unit. Our local maximum, the same thing. We're going to use our calculator or Desmos to find these points. We know our local maximum for this one is just this point right here because we can see that it's the only bump that we have. The only other bump that we have is down here, but this is more of a valley. So here is our local maximum right here. So in the calculator, you would go to Menu, Analyze Graph, Maximum, and again, you would highlight this point to find your maximum, or in Desmos, you can scroll over that point to see what it is. So using the calculator, this point is approximately negative 1.41, 9.66, and then for the minimum, the same thing. This is going to be 1.1441, negative 1.66. Now let's move on to example 5. So example 5, this problem is going to be odd because we see that we have 2 x's right here and we have 1 x right here. So if we were to multiply everything together, we would get 3 x's. So we are going to have an odd function. Our function is positive. which means as x approaches positive infinity, f of x approaches positive infinity, and as x approaches negative infinity, f of x approaches negative infinity. So again, if we were to put this in the calculator, we are going to get points approximately here, and our graph is going to look something like this. Our y-intercept, which we know is when x equals 0, we get to be 0, 2, which we can find in the calculator or on Desmos by either scrolling over the point on Desmos or in the calculator doing the same thing that we've done before. You can also press Control T to get the table to see this in the calculator. Our local maximum, or actually, sorry, our zeros are -3, 0, and 2, 0. You can see that our -3, 0, it crosses through the graph because this has a odd exponent, and this one, it bounces off the x-axis because of our even exponent. Our local maximum is this point right here, which we can find in the calculator or on Desmos as being -1.33, 3.09. And our local minimum, this point right here, is just 2, 0. Again, all of these points can be found in the calculator. About turning points. The graph of every polynomial with a degree of n has at most n minus 1 turning points. Let's think about our quadratic function, just because we just finished our quadratic unit and we know a lot about our quadratic function. We know our quadratic function has a degree of 2, right? Our quadratic function also only has one turning point. There's only one point where it goes from decreasing to increasing. So it makes sense to think of every polynomial's number of turning points is one less than the number degree that it has. So for example, if the degree is 8, there can be no more than 7 turning points. Alternatively, if there are 7 turning points, the lowest degree will be 8. If you look at these graphs here, this first one, we can see that we have 1, 2, 3 turning points, which means that our lowest degree would be 4. I'd like you all to complete this part of the notes on your own, and we will be going over it next class.